Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Richard Zeebe and David Hernandez with us today. Hello, Richard. Hello, David.
Hey,
Well,
David, let's start with you. What's your geolocation? Where are you at?
yeah, I'm in Taipei. It's
Hi.
9 a.m. currently.
Cool. All right. And it is, at least my Wednesday, September 3rd. So it's David's Thursday, September 4th. Very good.
Nice.
Let's see. It's still northern. How is the summer? Late summer anyway in Taipei.
Oh, it's super humid out,
Yeah.
but I think it's okay. Most places you go indoor have air conditioning installed.
I'm with you on that one.
Yes.
Because I'm in Phoenix, and very desert, but we are in our humid season, right? This is the season when Phoenix gets most of its rains,
Right.
monsoons and dust storms coming in. So we just got one the other day. So, but yeah, it's quite toasty. We were in the 39, 38 C's today or something like that. So very good. Richard is apparently in a lot more lush place than the desert. So, Richard, what is your geolocation?
I'm in Hawaii on the island of Oahu.
Oh, cry, cry, cry. I'm gonna have to go there some point. Very nice. Let's see. And how is the weather in Hawaii?
It's fine. It's starting to get muggy, as long as we have trade winds. So, May, June is pretty good, but then July, August, September, it starts getting muggy as well.
Mm-hmm. I gotta ask a question. Do you surf?
I do.
You
Longboard.
do. Awesome. How's the surf been this summer?
It's been okay, but too busy to go surfing. That's the problem.
Oh, when Jaws is rolling, you gotta go.
Yeah, I don't surf these sort of waves. So
Okay.
you need to be a pro to do Jaws. So I have a longboard and I enjoy the South Shore. That's okay.
Cool. Very cool. Very nice. All righty. And David, what do you like to do for research?
Yeah, my interest is in gravitational dynamics. I like to think about numerical methods. I like to think about things like time symmetric integration, chaos, orbital chaos, all that good stuff.
Very cool. Very nice. And Richard, what do you like to do for research?
We're mostly interested in solar system dynamics and long-term orbital solutions. So we try to calculate accurate solutions for the orbital changes over of the solar system, particularly Earth, over the last 100 or maybe even a billion years. And these solutions are being used in geophysics and the geological sciences.
Yeah, sure. Very cool. Very nice. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. No influence of passing stars on paleoclimate reconstructions over the past 56 million years. And Richard and David, take us away.
Yeah, so this paper is basically about passing stars and the influence that these passing stars have on orbital parameters in our solar system. And we are mostly interested in the effects on Earth orbit.
Okay.
And because you can think of passing stars as a tiny perturbation,
Mm-hmm.
and because of the chaos in the solar system, these perturbations get amplified over a long time scale.
Uh-huh.
So, I mean, even chaos in among our colleagues is often misinterpreted as complete disorder. That's not what chaos means. It
Right.
just means that it's sensitive to initial conditions,
Right.
and there are some things that are just unpredictable. And the orbital planets have been stable, or relatively stable, for a long time.
Uh-huh.
But if we look in at the details of Earth's orbital eccentricity, for instance, they start to diverge, for instance, after about 50 million years. So if you
Right.
think of passing stars as a small perturbation and you take two orbits, one of them is, say, a standard orbit and one is perturbed,
Mm-hmm.
then you see macroscopically after about 50 million years that they start becoming different.
Okay.
And this
Yes.
whole paper is really just about how long exactly does it take, from a small perturbation until we could macroscopically measure changes in Earth eccentricity, for example.
Okay.
Yeah. Just to add to that,
Uh-huh.
the solar system is chaotic just by virtue of it having more than two bodies.
Yes.
If it were two bodies, it wouldn't be chaotic. Once you add more bodies to the differential equations. It has to be. So it's
Mhm.
a general feature of our solar system.
Cool. Very good. I'm with you. I'm with you. Okay.
So if we want to, we can give you essentially the take-home message up front.
Okay.
And I think that would be figure 4 we can first have a look at.
Yeah, let's slide down to figure 4 and figure 3 and figure 4. We've got number versus a time scale. Okay.
Yeah. So what we see here on the x-axis is the number of simulations that we ran for this project.
Okay.
And on the y-axis, we see what we call divergence time. So what I just mentioned is after about 50 million years or so, you start these small perturbations, for instance, from passing stars, to
Mhm.
show up in the actual difference in the eccentricity.
Okay.
And the question we are trying to answer here, after how many million years exactly?
Okay.
And based on our study, and we used a relatively complete solar system model, all
Mhm.
our simulations indicate that it takes more than 56 million years until we can basically detect these changes in Earth's orbital eccentricity. So
Okay.
if you look at the top here, you see these blue diamonds, the green squares, and the triangles.
Yes.
And all of these simulations, they yield divergence times, tau, which are longer than 56 million years.
Yes. So here.
And the reason for this is, and you see also on the left hand here, on the y-axis about 40 million years. So these are these red triangles.
Uh-huh.
These are simulations in which we actually used a simplified solar system model.
Okay.
And the whole point of this paper is that you need to have an accurate physical model to calculate the accurate taus, accurate divergent times.
Okay.
And if we, for instance, in our model, we do include asteroids, we include the
Okay.
J2 of the sun, so the quadrupole moment of the sun.
Yep.
And particularly important, we include a lunar contribution. So the moon really makes a difference. And in the previous study that actually ignored the moon and the solar quadrupole moment,
Okay.
they found divergence times, and these are similar to these red triangles here,
Or
that are smaller or less than about 56 million years.
Mhm.
And the take-home message here is that if you actually use a more complete solar system model, you get longer divergence times.
Okay.
It seems funnily that the moon has some sort of stabilizing effect on these divergent times.
Mhm.
Yes.
David, do you want to add to this?
Yeah.
Yeah, well, just to say, we could see from the plot the effect is pretty significant,
Yeah.
which you may not intuitively expect. Thinking about the moon seems like a small perturbation or J2, but
Even,
yeah.
yeah.
So the point is, yeah, good physical model, good numerical method, which Richard and I have worked on other papers, is important too, but that's not the focus here. But these things have a surprising effect in this case.
So let me ask one question. Maybe it's a detail, but you mentioned, the divergence times here are measured by some change in the orbital eccentricity. And is there some threshold above that change in E that one uses?
Yeah, we
Yeah,
can
I,
we
I
can go
was
to. Oh, sorry.
yeah, I was just going to say we can just go to the previous plot, I think,
Ah, okay.
to discuss.
Ah, okay.
Yeah,
Ah,
go
here we
ahead,
go. Okay,
Richard.
yes, yes. I'm with you. Okay.
So if you look in the top panel, this is actually a plot of Earth eccentricity, which you can calculate with our solar system models. And
Hmm.
so the blue line is a solution that is what we call our standard solution. We have done these calculations in 2018,
Yep.
and they are labeled ZB20A, ZB18A.
80,
And if you look at this is the represented by the blue line. And now, in addition to this, we're showing one simulation in which we have included a number of random passing stars,
okay.
as well as one particular passing star, which is from the Gaia database, as the star is HD 7977.
Hmm.
And the question is, so this was a close encounter, I think, 2.7 million years ago.
Okay.
And if we include these in the calculations, at what time in the past, for instance, would that be detectable? And if you look at the purple line in the top plot, you see that at around 70 million years it starts, and then clearly at 70 million to 72 million years ago, the
Yeah.
solutions are very different.
Yeah.
Right? So this is where we
Okay.
pick
Okay.
our divergence time, where we could macroscopically actually pick a date and say, if this had happened, and you would try to reconstruct and compare our solution to actual geologic data, we
Yes.
could tell which of these solutions is right and which
Got
is
it.
wrong.
Got it. So there's a experimental sort of basis behind choosing that number for
Yes,
that.
yes.
Good. Excellent. I'm with you. Hmm.
We could also look at other every orbital element. Well, many orbital elements are diverging, uh, but in this particular case, this one is especially useful, eccentricity.
Yeah. Good. Good. Very good. Yeah, the state vectors will all change. Uh-huh.
Yeah, particularly because we actually have geologic data from which we can compare eccentricity. Like we other parameters may be more difficult. For instance, inclination is something that
Yeah.
is not really recorded in the geological record, but
Okay.
eccentricity and the frequencies are. So we can actually compare this to data.
Very nice. Beautiful. Beautiful. Okay. And what we got on the low? This is just the difference between the two.
Yeah,
Yes.
this is just on a log scale. So the upper plot, the top plot shows that both the two solutions um, um, uh, on a linear eccentricity scale.
Yes.
And then the bottom plot is just showing the difference on a log scale between the maximum.
Cool.
And what's important there is, as I mentioned from the top panel,
I'm
you
with you.
could pick the divergence time tau at around 70, maybe 72 million years.
Uh-huh.
And this is the black arrow in the bottom. And
Mm-hmm.
now the important thing
Yep.
is this divergence time longer than 56 million years? Because there is an important climate event at 56 million years. And this is labeled in the bottom plot here by the acronym PETM.
Uh-huh.
And so PETM means Paleocene, Eocene, thermal maximum.
Yes.
And
Okay.
that's a climate event. That's a big climate event in the past where the average surface temperature of the Earth increased by 5 to 8 Kelvin,
Huh.
and it's marked in the geological record. And the important question about this climate event, the PETM, is whether or not our orbital reconstructions would be different if we would include passing
Ooh.
stars or not.
Right. Right.
So
Right.
the big question is would our understanding of this climate event based on our models be different if we include passing stars or not?
Okay.
And our answer is no.
No. Right.
Yes. So just to clarify, from looking at this plot, we see a dashed line,
Yes.
and kind of the definition of tau is when that blue curve, we say irreversibly crosses that dashed line.
Gotcha.
The irreversibly is not supposed to be taken formally. You can't prove that for infinite time. That's
Right. Right.
it's going to stay up there. But yeah, kind of once we see
Fair enough.
a divergence that increases past that point.
Gotcha. Hence the term divergence timescale. Okay. Very cool. I am with you. Very good. Thank you for answering the question I should have waited for. Okay, where do you want to go to? Want to go to figure one? You want to cover some of the equations? What do you want to do?
Yeah, we can go to the top.
Okay, let's go to the top.
Yeah, I think the first interesting item is actually figure one. Can probably go to figure one.
Doing some impulses here. Boop, 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 boop. And
Yeah. All right.
impulse.
Yeah, you can show this is based on some estimates. So if you show equation one and two,
Okay, let me
uh,
just show that real quick.
right
Okay,
there, just up there, this
impulse.
has been used since Oort in the 50s, and the one is the impulse. You can look at comets that are impacted by passing stars. That's equation one, and the impulse gradient, which is divided by the smallest distance between your impactor and say the Earth or the solar system. That's a parameter D, also called impact parameter. That's something like the impulse gradient.
Yes.
And I want to emphasize that we did not use these equations to calculate anything properly in this paper,
Okay, yes.
because of the chaos, you have to do full numerical integrations. We're
Mhm.
only
Yes.
putting these equations and figure one in there for illustration. So it shows you basically what you need for a large impulse gradient or a large impact on the solar system based on these estimates, and what, for instance, you would get if you do use random parameters. So the question is, do randomly passing stars have a rather small or rather large effect on the solar system?
Yes.
And, just to illustrate this, we use these equations, and this here is actually the impulse gradient.
Okay.
So the x-axis here, or the front axis, is the impact parameter, so the distance of closest approach.
Mhm.
And then the bottom y-axis is the mass of the passing star in solar masses.
Yes.
And the z-axis is the impulse gradient.
Yes.
And
Uh-huh.
so you can estimate, when, at what impact parameter or impulse gradient would you have a large impact that would
Mhm.
disturb Earth's orbit, for instance. And you need quite a large impulse gradient. So think, for instance, at an impact parameter or d of about 1,000 AU and one solar mass, that would be a really strong close encounter.
Yes.
So this is something that you would need to have a significant impact.
And presumably you would see that in the geological record.
That if we had a close flyby like this, probably in the order of 1,000 AU and maybe solar masses, and up from there, we might be able to detect it.
Okay.
But if you look at these orange dots in the front, so we
Yes.
just plotted the impulse gradient for randomly picked stars in there. Most of the flybys, most of the encounters are actually weak.
Yes.
So most of these impulse gradients, as you can see, are relatively small.
Yeah.
There's one impact from the star that we discussed before, which is, I think, on average, something like 39,000 AU.
Okay.
No, I might be mistaken. I think the 5% likelihood is something in the order of 3,900 AU.
Okay.
And that is one we actually tested. So despite that not being, a very large encounter, that's probably the largest encounter you can get from the Gaia database within the last maybe 5 to 10 million years. And that's the one we simulated, and we still didn't find a significant impact on Earth's orbit over 56 million years.
Okay. Cool. Yes. Good.
Yeah.
Let's go. Good.
Yeah, just to piggyback, emphasize what Richard was saying, due to the inherent chaos of the solar system, even though we present those equations, it doesn't mean that propagates one-to-one to an effect on Earth because of the long-term, could say, predictability.
Yes.
Or
Chaotic nature.
Yeah.
Yes.
Yes. Yes. Indeterminate. Yes. Very good. Lots of words for that. Uh-huh. Okay. Very good. Okay. So this is using some of those, or those equations anyway, those simpler equations. Okay. Maybe we want to talk a little bit about what we do in these integrations.
Yeah, so again, the equations, this is the stellar flyby parameters that we use to do our simulations, but it's easier to look at the next figure, which just shows essentially these parameters. And what we did is we ran several tests. So for these random stellar flybys,
Okay.
you can use different estimates, and we used three different sets of flyby parameters. And so in the top panel here, so the three top plots, they are based on the paper by Heisler et al. In 1987.
Uh-huh.
And you have to pick parameters, based on best observations, of course, for your average velocity or speed distribution. So it's essentially Maxwellian.
Yes.
Then you have to have a distribution for the mass of the flyby. And so this is again on the y-axis is the frequency, right? So number in a certain range.
Yep.
And as you can see, most of the flybys, the x-axis here is solar masses,
Thereabouts.
are below 1.5 or maybe one solar masses.
That's the only
And then
one. Mhm.
and then we injected essentially random flybys within a sphere around the solar system of 1 parsec, and then used random orientations and random velocities picked from these distributions
Okay.
to see what impact we ultimately could have on the Earth eccentricity.
I'm with you.
And so the top row, the top three plots is from Heisler
Mhm.
et al. 87. And then there are several other papers who used slightly different parameters. For instance, we picked another paper by Garcia et al. 2001. But as you can see, the distributions are slightly different, but not tremendously.
Not too much, yeah.
And then the third parameter set is from a package that from Garrett Brown.
Okay.
And you can just use that package and generate random parameters for speed, mass, and for impact parameters.
Yes.
And so we just to make sure that we're not, picking one particular example that is maybe very weird or very strange compared to other options. We tested all three of these parameter sets,
Cool.
and basically it didn't make any significant difference which one we picked.
Yeah.
Yeah. Yeah, and it was important to do something like this because the final
Yeah.
result is so surprising.
Yeah.
Or I think so. So this, three independent sampling methods adds confidence to the result.
Right. Gives it a certain robustness. Yes. Right. Very cool. Okay, so we got our distributions. There we go. And you definitely want to take care of peculiar velocities. We discussed the three packages. We talked about the divergence time test scales. And there we go. So three, and we covered four. And how about five?
Yeah, and so essentially we've since we've already given the take-home message, once we did all these simulations, we did 3 times 128 on a supercomputer and tested all these three different parameter sets. And what we found was, and that's why David says it's surprising, these parameters had very little influence on the actual outcome. The most important thing is the solar system model. And because we included a lunar contribution or something related to the moon
Right.
and J2, our divergence times are much longer.
Okay.
And so that was shown in figure 4.
Right.
And also importantly, we tested, for instance, is there any influence of the initial conditions, right? So for instance, if you look at
Oh, yeah.
these are purple diamonds, they are labeled Heisler 87.
Yes.
And we varied
Emma.
the mean anomaly of each body by a tiny little bit before we did the simulations.
Okay.
So essentially at T0, you randomize your initial conditions by a tiny perturbation. And we wanted to show that even this does not have any significant influence. The only thing that matters here for the differences is the physical model.
Yes.
So even if you
Yeah.
randomize initial conditions, it does not change your divergence time.
Awesome.
Yeah. The reason to do this was, I think this is exactly what previous authors did to randomize their initial conditions. So we wanted to exactly match that. I believe that's what other authors did, right, Richard?
Yes,
Delta
one of
M.
the reviewers mentioned this, and so we added these simulations, which is a good thing, I think.
Very cool. Very cool. Very nice. And there are three awesome appendices people ought to check out if you want to walk through a little bit about the scaling and
Well,
integrators.
yeah, well, I was going to say, Richard, we didn't even talk about Orbit N. Maybe we should mention that this was run with Orbit N, your integrator.
Yep.
Yeah, that's the
you wanna-
integrator that I've written, and it includes all the important features that we need for our numerical simulations. And it's open source, so if anybody interested,
Nice.
it's a C code, but you don't have to do a lot of programming to use it. You can use
Very
an
cool.
input file. It's relatively easy to use, and it has solar quadrupole moment. You can easily include asteroids. It has a good and fast general relativity implementation, and of course, it has a lunar contribution.
Yes. Yes. So let me let's see. On any given run, how long does that roughly take? Wall clock time?
You can run it on your laptop in 2 days.
2 days. Okay, on a laptop.
Yeah. So the critical thing here is the number of simulations. It's
Yep.
The computing resource for a single run is not that terribly large, but because we need ensembles, we use an HPC system.
Yep. Very good.
Yeah.
Very
So just to put Orbit where we're using Orbit N in context, this is similar to, for example, in Rebound there's WH fast, but
Yes.
Orbit N really has some new physics that's not in other codes. But other options are Mercury.
Yes.
So all of them have the basic algorithm.
Yes.
Yes, which is basically the Wisdom-Holman method, and that's the basis of Orbit N.
Very cool. Very nice.
Yeah.
Beautiful work. Beautiful work, Richard and David. Thank you so much for walking us through your very lovely HA article. Cool.
Yeah, thank you. We can briefly go through the appendix too.
Oh, if you like. Sure.
Yeah.
Let's go down. Which one we'll cover?
Well, do we want to say anything about A and B, Richard, or?
Yeah, you can talk about the applicability of wisdom hormone.
Yeah, sure.
Okay, sure, sure. Yeah, basically, we wanted to be as careful as possible with this work, and part of that, the basic method, Wisdom Holman, makes some assumptions about the strength of perturbations between planets, between close encounters. So it's just for completeness, making sure that even in the presence of a close encounter, those assumptions of the numerical method don't break down.
Yes.
So basically, all of these are checks to make sure we're not going incredibly wrong somewhere.
Cool.
And I think Richard also even checked some results with Buehler-Stower,
Ah,
right?
for
Right,
another there.
Richard?
Not in this article, because
Oh,
the
oh,
integrations with Bullard take a very long time, right? Because they do have adaptive step size, but integrate is much slower.
Yes.
okay.
Yes.
Yes. Yeah, besides this, I guess maybe we've covered most everything.
Okay. Very cool. I'm still going to say awesome work. Very cool. It's a lovely paper. Check it out, people. All righty. Cool. Let's see. So you mentioned it a couple of times, and it's actually part of your take-home message. So let me push on a little bit. And if getting the right detailed physics model of the solar system is important, what do you think are the next steps where we go from here? Might want to include J2 of the gas giants or something of those orders, or just sort of next steps. Where do you think we go? Because I don't think this is the final article on stellar flybys.
Yeah, so one of these things that we also mentioned in the conclusions of this article are really long-term integrations over giga years.
Ah,
And it's very clear, and we understand that you have limitations because if you want to integrate over, say, 4.5 billion years, you have to make compromises, right? So this model, I said, you can run it in 2 days for 100 million years, but it's linearly scaling. So if you run several giga years, these computations become expensive, and particularly if you use ensemble integrations, you would need a lot of computer resources to do this. But the
mhm.
big question is, and there's a bunch of papers out there that have looked at the influence of passing stars on the solar system over its lifetime. So if you look at 4 or 5,
Good.
4.5 billion
Yeah.
years, the question is how accurate are our conclusions based on simplified models? We do have to use some simplifications, but the question is, if we include more sophisticated models and say the moon or J2 of the gas giants
Hmm.
or even asteroids, we have not run asteroids over billions of years because it's too expensive.
Okay.
We are wondering what would be the outcome. Do we, for these sort of estimates, do we need more sophisticated models on the giga timescale? Yes or no? So this would be certainly one area we'll be looking at in the future.
Nice. Very cool. Very cool. Want to add anything there, David? Where you think things might be going?
No, I think that's a pretty good direction.
Cool. All
Nothing to
right.
add.
Well, it'll be really exciting over the next couple of years as you guys investigate this because it'll take that much CPU time or something. I don't know. But it'll be really exciting to see the fidelity of the physics that goes into these flyby calculations and the impact on the geological records. It'll be really cool to see over the next couple of years. So very good. All righty. Thank you once again, Richard, David. Thanks.
Thank
And
you.
yeah, and that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.